Hello everyone, this is Dr. Webb, and welcome to the next Calculus 1 video. So in this video, we are going to be looking at all the ways in which continuity can go sour. And so these are what are called discontinuities. So let's just recall definition of continuous. We talked about this in the last video. So we say that a function is continuous at x equals a if the value of the limit as the function approaches a is equal to the actual value of the function at a. So this is the limit as x goes to a, and this is the value of the function at a. So the limit and the value match up at a. So what does this mean? So what does it mean for it to be continuous? Well, since we have the limit there, that means that both one-sided limits for f of x exist. And more than that, not only do they exist, to have the limit as x goes to a, those two-sided limits have to equal each other. And then what are they equal to? The value of the function there. Right? And so really when we're talking about continuity, really we're breaking this down to thinking about the two one-sided limits are going to the same place and they're going to the value of the function. So now let's think about all the ways that this can go wrong. So what possible ways can this not happen? And so we're going to kind of focus in on starting with this last connection and sort of work backwards from there. Okay, so let's suppose that the limit of the function exists as we go to a, but the limit does not equal the actual function value of a. So this could be that either f of a doesn't exist, or it's just something different. And so since the limit exists as we go to a, this means that the two one-sided limits both exist and they go to the same value. It's just different from what the actual function is at x equals a. So what does this look like in a picture? Well, so these are times when you have a hole and you have a nice function and then it has a hole in it at that spot, right? And so if you look in this picture on the two one-sided, as we approach a from the left, we're going up to L. And as we approach a from the right, the values of the function are going down to L. But right at a, we've got that spot missing. And so it might be that the function's not defined there. It might be that it's just some other value off right there. Okay. And so the idea here is that we could fix this continuity, this discontinuity at this point, just by changing the value of the function at a. So if we set f of a to equal L, so we are changing the value of the function at a to be L, the limit that we got from the two sides, then we'd have continuity. That's all we need to do to make this continuous at a. And so since it is so easy to remove this continuity just by essentially filling in that dot, we call this a removable discontinuity. So it's removable because we can fix it just by filling in that hole, and then it's gone. And now we have a continuous function again. Okay, so then the next thing that can go wrong is, let's suppose that we still have values for the two one-sided limits. So on the left it's going to L, on the right it's going to K, but now these don't line up with each other. So there's a break between these two. So the two limits both exist, and they exist as real values, but they are not equal to each other. So what's that going to look like here? So there's some gap between them. And so here's an example of what we're talking about here. So the limit on the left as we go to a the function is going to this value L. So L here is equal to the limit as x goes to a from the left. Remove that minus 1 of f of x. But when we approach from the right, the function is going to some other value. And so this k here, this is the limit as x goes to a from the right of f of x. And there's this distance here, this gap between it, and we're going to call this gap a jump. So as we go to a to the left, we're going towards L, and then whatever happens at a happens, but then after that point, once we're on the other side of a, now we're close to k. So the function has made a jump instantaneously from being at about L to about k. Okay, and so because of that jump there, we're going to call this a jump discontinuity. So we say f of x has a jump discontinuity at x equals a. So what can happen that's beyond this? Well, let's say still we have these two limits, these two one-sided limits existing, but at least one of them is no longer going to a real value, but instead is going to plus or minus infinity. Okay, and so remember, when we have limits going to plus or minus infinity, that's when we're talking about having asymptotes. So what would this look like? So here on this side, we have both sides are both going off to infinity. Right, as we approach a to the left and to the right, in both cases, function values are getting bigger and bigger and bigger. And so what are we left with? We have an asymptote in between, and that is really the signifying thing that we can find when you have a vertical asymptote. You have this type of discontinuity, and so what are we going to call this? We're going to call it an infinite discontinuity because at least one of the limits is going off to infinity. And they could be both going off to positive infinity. They could be going off to negative infinity. You could have one going to positive infinity, one going to negative infinity. You could have one side going to positive infinity and the other side going to 7. So long as at least one of the one-sided limits is going off to infinity and the other limit exists in some way, then that's when we have an infinite discontinuity. And then what else can happen beyond this? Well, if the limits don't exist and don't go to infinity, that means at least one of them does not exist at all. You can't even imagine, you can't even come up with one value that it's going to. And so that's where we have some real craziness going on in the function. And so here's some real craziness. To the left of the function, if we go to the left, the function is going to some value right there. We can call it L. But on the right, we have it oscillating wildly and not going to any value at all. So going this way to the right, the limit does not exist. So limit as x goes to a from the right does not exist. And to a large degree, these are sort of the worst type. You can't really fix these at all. Even if, infinities, you can kind of maybe divide off by another infinity to get it to cancel off. This isn't going to work for these. The function is just too wild on one side. And so since there's nothing really to fix it, we call this type of discontinuity an essential discontinuity at x equals a. Okay, so to close this video out, have a picture of a kind of a wild function here with a bunch of discontinuities. And so let's talk about what type of discontinuity is happening at each spot. So let's start moving from the left to the right. So the first discontinuity we see is happening at x equals minus 4. And so what type of discontinuity is this? Well, as we approach minus 4 from the left, the function's going up to 4. As we approach it to the right, it's also going up to 4. So the two one-sided limits, they both exist and they agree with each other. We just have a hole right there. And so all we would need to do to fix this is to move this value at minus 4 up to fill the hole, and then we'd have a continuous function again. So what type of discontinuity is that? Well, this is where we have a removable. We can remove it just by changing the value of the function at that one spot. Okay, now let's look at x equals minus 1. Now in this case, as we go to the left towards minus 1, our function values are going close to 1. But as we go to the right to minus 1, the function values are going up to 2. And so there's this gap, this jump between them. And so what type of discontinuity is this? This is a jump discontinuity, because the values of the function instantaneously jump as we cross over minus 1. Now our next discontinuity, we're looking at what happens at x equals 1. And so on one side, as we look to the left, the function's shooting off to infinity, and we have an asymptote there. To the right, it's going towards the value minus 1. And so the asymptote here is the dead giveaway. When you have an asymptote, when you have at least one side going off to positive or negative infinity, this is an infinite discontinuity. And last but not least, we have a discontinuity at 4, x equals 4. And as you see on the left side, things are behaving, rather well. It's going off to about 3.5. But on the right side, this is total craziness. It is not going to any single value. It's just wildly oscillating up and down as we get closer and closer to x equals 4. And so the limit of the function as x goes to 4 from the right does not exist. And so that means that this is an essential discontinuity. So that is all for this video. I will see you again soon.